with a background in statistical solid-state physics, complex systems, HPC and machine learning. His group at Helmholtz-Zentrum Dresden Rossendorf is helping to better understand laser-plasma interactions by solving inverse problems in measurement data. And in his talk, he will discuss how to close the loop between simulation and experiment in plasma and photon science.
Thank you for the introduction. So, yeah, already heard the thing. I would like to give you a small overview over some of the challenges we are facing there in plasma and photon science. So here, what you can see here is basically a beamline for where you have laser plasma acceleration or laser electron acceleration specifically using this laser backfill acceleration process, where a laser shoots basically a target, which then produces fast electrons, go into this beamline, and for example, the use of this is shown here as being a secondary radiation source. So basically, you want to have a free electron laser where you have like a very relatively small acceleration stage for your electrons. So you can basically build more of these devices in order to be able to do like more material science, for example, using an X-FEL. And there are a lot of challenges in our group that we are working on here. A lot of these are basically inverse characterization things or inverse control things. So like, for example, stabilizing this laser or being able to create specific spectra, light spectra in this laser on demand. Then there are things like, for example, characterizing how does this dynamics look in here, for example, directly by imaging, also using another current X-FEL. But then there's also, for example, the problem of learning about what is actually coming out of this acceleration process. So what you can see here is basically a picture of how it looks like in the simulation. It's a bit hard to image that in the experiment because that's like a micrometer scale thing, and also getting the 3D information in these kind of picoseconds that it happens isn't that easy. What's coming out is an electron bunch that often have like a more complex form. That you can see here is basically some micro bunching characteristics. So it's actually not one bunch, like it's multiple bunches. If you look in more detail, and there are different stages where some things about the electron bunches coming out is measured. For example, there are these imagers in here where basically electron bunch goes through these imagers that are fluorescent foiled. You see patterns like these that are coming out. And basically, you can, for example, turn these things in phase space by going through this beamline and kind of get different projections out of different places of the beamline, try to reconstruct from that, which gives some amount of information, but is often insufficient to kind of get like this micro-bunching structure there. So I want to talk a bit about the nice connection to the previous talk. So what are we facing here in the experiment? We have the our input parameters that are basically parameters of the laser, parameters describing the plasma jet, like how density of how much is gas is flowing there. And the output, basically, that what you can measure is like radiation, for example, coming from the undulator, or just energy spectrum of the electron bunch, or these transition radiation of fluorescence here. Problem with these is often at the input side, we have a limited resolution of what we can actually set and limited fidelity and how we can control it. Like, for example, the spectrum of the laser, we control it in one place of the laser beam. We can't control it in the full cross-section of the beam. And also these measurements are often low-dimensional projections of basically this thing, which is depicted here in 3D, but actually what we want to control it actually in its six-dimensional phase space. So we want to basically know that how everything is moving along the beamline, how fast, so does the velocity distribution there, and basically also what's the divergence, how far electrons going apart from each other. And one issue here also is that we, due to having a flowing gas jet here and also the laser, we have a high shot-to-shot variance, so we can't just repeat shots with the same settings to get clear statistics because there's a lot of noise in those things, so we would get a very blurry image when we just average over everything. So we have a problem with like having noisy input, noisy output. So just having a lab in the loop in this case doesn't work like that. It's first you have to understand what's the lab actually doing on a shot-by-shot basis. What we can have in the loop, what you want to do there is to actually then understand this LPA process to actually be able to control it. But we can't directly look inside in the experiment. And what we can have in the loop is the 3D simulations which in this case provide us full information about the thing. So we can set any laser pulse shape we want in principle, and we can we get the full particle phase space out. So we have full information at the cost of high computational cost. But this we can have in the loop, though we can't also run a lot. So Bayesian optimization is definitely a thing we also look into there. And now what I want to talk about is actually how can we connect these noisy observations with our simulations, of which we can't do many most of the time, and yeah, are higher dimensional than these observations. So I already mentioned that we are solving a lot of inverse problems. This example has two of them. So basically what we have here is basically we want to go from what we observe at the beamline. This is an example of so-called coherent optical transition radiation, where we have multiple wavelengths of radiation emitted from electrons going through a changing their medium. And that gives us some more information about the bunch. From that, we want to go to the actual shape of the bunch. And when we have the actual shape of the bunch, we would like to know what are these parameters that lead to the parameters for our experiment that lead to this shape. So the thing what we know about is actually the propagator, how we measure this thing. And in this other case, we have the simulation, that direction, so that would be forward direction. What do you want to know, what do you want to go backwards? So first I want to talk about physics-informed reconstruction from this radiation, where we basically actually use the physical information that we have about this propagator, and we basically have a self-consistency loop where we say we give a proposal for this bunch shape, which is generated by a neural network here, so we can also sample multiple solutions. Have a propagator, and we compare the result with the input to then iterate and fit this. We can condition the network that we have there on the input to basically just directly learn multiple solutions and not just have like something akin to a normal gradient descent. And this then leads to results like this. So basically we get something close there. Still the system is actually under constraint. Ideally later we will include other modalities to kind of constrain it. At the moment what you can see here is we, for example, put some explicit physical constraints inside, so because we know that, for example, certain distribution in z direction would be should have a certain shape. When we then construct a large data set of that, we can basically get the distribution of these results, because we don't actually know what the electron bunch shape is that we actually get in the experiment. We can do some simulations, but these parameter spaces don't necessarily need to match. So we can, with this, actually constrain our parameter space and figure out where do we need to run our simulations. So, and with these, this knowledge about the relevant bunch shapes, we can go into the simulation. Basically actually doing the inversions for a far-term goal. I want to talk about one step that we actually did here, is basically setting up a workflow for in-transit training on these large simulations. Why in-transit training? Because these simulations can produce a lot of data, and if we want to kind of produce a also high-fidelity surrogate model of these things and learn the distributions of shapes that are coming out of there, electron density that's coming out of there, we don't want to can't necessarily store all the training data on disk, due to bandwidth limitations and also just storage limitations. So basically have an online consumer where we directly stream the data into a neural network for training. There are different ways of kind of tuning this performance-wise, which is what we are working on. And we did a proof of concept for this with in this case, different physical problems. They have Helmholtz instability, so we have two flowing jets of charged particles going past each other. We have these separation planes, and instability forms, and we have these vortices forming there. And there we can do a lot of things. For example, we can have this inversion of a physical reduction. Basically, we measure this radiation under a certain angle, and then we want to go back to basically see where did this radiation come from, and what process inside the plasma did actually make this process happen. That's like also in the LWFA, like which piece of the thing irradiates, like a certain of this bubble irradiates some radiation. And also the compression-decompression thing, kind of getting latent representations of these plasma dynamics in order to have approximations, to have like coarse-grained approximations of the simulation in order to speed it up step by step. And also learning basically surrogate model of forward prediction, for example, for the radiation. And we came up with this model that basically does all three of these things. So we have an autoencoder, but we have example, this inverse problem, where we go from the radiation through the particles that are there. In order to be able to produce this particle cloud, we have basically this autoencoder which learns latent representations of the particles, which then this invertible neural network can predict. And the forward direction of this gives us a radiation surrogate. So the data here is not stored, not repeated in time, in order for the network to not forget what it has learned over the simulation time, because in this case we just stream from one simulation, this experiment, not like an ensemble, so we don't actually transfer, we just extract patterns from one run. And so we use experience replay to basically have a buffer of some of the earlier samples which we always mix in. And the results here basically show that the network has learned to classify these different, or not classify, not classification problem, but in a way it has learned to basically map from these, map these radiations from different dynamics backwards and forwards to the particle dynamics that's going on in a certain region of the thing. And then we have, for example, a vortex region, or we have like high radiation, and it also learned basically about the Doppler effect here, because if the flow is going towards or away from the receiver, we have this blue shift or red shifting of the radiation. There's a bit of a problem with the decoder part of that for the point cloud that doesn't actually give the correct or very high fidelity results yet. That was a best paper candidate at the IPDPS 2025. With that, I would like to thank my team and thank you for your attention.
Thank you for the presentation. Time for questions. So when I look at this, of course, I'm wondering, okay, what can I learn from this in applying this in other domains where I also have imagery, or physical fluid dynamics, or also these inverse problems. Can you comment on that? How this could be transferred? Yes. What are maybe limitations or requirements for transferring this to other domains?
In imaging, for example, there is the thing where we have this physics-informed learning. That's not our idea. That exists before, for example, for holography, that has been widely used in there. But for example, things like the papers like PhysiNet, PhaseGun, that basically use this physics-informed loss to train things. This is for holography. And that can, in this way, if you have a differentiable forward function, be easily transferred. If your forward function is not differentiable, that we will probably also look into the future to use instead reinforcement learning with the same thing. But at the moment here, we have a physical forward function, so we use that. And that can be transferred and used in many physics domains where you do have a physical forward function that you can use, and ideally it's differentiable. So, and the streaming part, whenever you have high data rates and you want to ingest those, this kind of more is a specific thing when you have large-scale simulations where you do want to learn about the shape distributions in there, and you have to run these things at high resolutions, and then basically have to learn a downsampling of the thing on the fly. So that does transfer, but mostly to similar domains that also kind of fill up supercomputers with large simulations. So maybe a bit more limited.
Any further questions? So then let's thank Jeffrey again.